Hello everyone. Today we are going to present on the topic Instruction Decoder Circuit Design from Opcode to Operation. This presentation is presented by Rakavi and Anuja from the Department of Computer Science and Engineering. In this session, we'll explore how the CPU decodes binary instructions into meaningful control signals that make the processor perform the right operations. Let's begin.
In computer architecture, one of the most critical steps in executing an instruction is decoding. The instruction decoder is responsible for interpreting binary instruction codes fetched from memory and translating them into control signals. These control signals direct the CPU's hardware components like ALU, registers, and memory to perform specific operations. A well designed decoder ensures faster, more accurate, and efficient execution of every instruction, which ultimately improves the overall performance of the system.
What is the of the decoder in CPU architecture? The instruction decoder plays a vital bridging role between software and the hardware. It acts as the translator that converts program level commands into electrical control signals. For example, when a program requests an addition or a move operation, the decoder identifies it from the opcode and signals the ALU or the registers accordingly. This ensures that each instruction reaches the correct hardware unit at the right time, maintaining synchronization and enabling seamless CPU operations.
Why need for instruction decoding? The CPU cannot execute binary instructions directly because they are just patterns of zeros and ones. The decoder is needed to translate these binary opcodes into meaningful control logic that the hardware can understand. This process ensures proper coordination between all CPU units such as ALU, registers, and memory. Without decoding, the processor would not know what operation to perform, leading to inefficiency and errors. Thus, instruction decoding is what makes the binary code actionable.
How actually does the instruction cycle work? To understand where coding fits in, let's recall the basic instruction cycle. Every instruction goes through four main stages: fetch, decode, generate control signals, and execute. In fetch, the CPU retrieves the instruction from the memory. Decode, the opcode is interrupted by the instruction decoder. Generate control signals. Signals are produced to activate the right components. And finally, in the execute, the instruction is carried out by the hardware. Among these, the decoding phase is the most crucial because it determines what operation is to be performed next.
This block diagram shows how the instruction decoder fits within the CPU architecture. The process starts with the instruction memory, which sends the instruction to the instruction register. The instruction decoder then takes the opcode part and interprets it. It generates specific control signals that guide the ALU, registers, and memory to perform the required operations. Every block here works in harmony to ensure the CPU performance instruction efficiently.
What is the working principle of the instruction decoder? The working of the instruction decoder can be summarized in a few key steps. The instruction is fetched from the memory. The opcode bits are separated from the instruction. The decoder logic examines the opcode and identifies the type of operations. It generates a set of control signals corresponding to the operation. Finally, the CPU executes the instruction based on those signals. So, essentially, the decoder acts like the CPU's interpreter, converting binary code into meaningful hardware actions.
Now, let's look at the circuit design concept behind the instruction decoder. Most decoders are based on binary to one hot design. This means for every unique binary input, only one output line becomes active, representing a specific instruction. For example, if we have a 4-bit opcode, it can produce 16 possible outputs. Each output corresponds to a unique instruction like add, sub, and move.
Here is how it works practically. When the input opcode is 0, 0, 0 and 0, the first output line, let's say 0, 0 becomes high, representing NOP, that is no operation. When the input is 0, 0 and 0, 1, 0, 1 goes high, which could represent an instruction and so on. So the following instruction like sub, multiply and move takes place in the same manner. The binary to one hot decoder provides a clean, fast, and efficient way to translate machine instruction into actions. It's the backbone of instruction selection in the CPU's control unit.
To understand the decoder's logic more deeply, we can represent each output using Boolean equations. Let's take an example of a 4-bit instruction decoder with inputs A, B, C, and D. Each output line corresponds to one unique combination of this input. For example, 00 is equal to A apostrophe B apostrophe C apostrophe D apostrophe. 01 is equal to A apostrophe B apostrophe C apostrophe D. 02 is equal to A apostrophe B apostrophe C D apostrophe, and 03 is equal to A apostrophe B apostrophe C D. Here, the apostrophe denotes not, meaning the bit is 0. This ensures that only one output line is active for any particular input combination. These Boolean expressions can be implemented using AND or NOT gate in hardware. The result is a circuit where the correct instruction line goes high depending on the binary opcode. This output is then sent to the control unit, which then triggers the appropriate hardware components inside the CPU.
Next, let's see about the implementation methods. The instruction decoders can be implemented in several ways depending on design complexity. Hardware implementation. Using a standard decoder IC like the 74LS138, which performs binary to one hot decoding. HDL design. Using hardware description languages like Verilog or VHDL, which allows simulation and testing in FPGA or ASIC platforms. Microprocessor integration, where the decoder is built directly into the CPU's control unit for compactness and high performance. Each method has its own advantages, but the goal is always the same: efficient decoding of instruction for smoother operation.
Integration with control unit. The instruction decoder is directly connected to the controller unit, which coordinates all the CPU's actions. The decoder's output signals drive control lines that determine what happens inside the processors, like activating the ALU, reading from or writing to memory, or selecting specific registers. This tight integration ensures that as soon as an instruction is decoded, the right components are immediately triggered for execution.
Applications. Instruction decoders are used in a wide range of systems including CPU control logic generation, microcontrollers and embedded systems, instruction set decoding in advanced processors, and FPGA or digital circuit design. Essential, any system that executes binary instructions need a decoding unit to translate machine code into hardware actions.
The main advantages of instruction decoders are they allow fast instruction identification, making the CPU more responsive. They have a simple and reliable logic design which improves efficiency. They are easily scalable, so new instructions can be added as processors become more advanced. Because of these qualities, the instruction decoder is one of the most important building blocks of any processor.
To conclude, the instruction decoder is the heart of the CPU's control logic. It converts binary opcode into the control signals that drive execution. A well-optimized decoder ensures that instructions are executed quickly, accurately, and in perfect synchronization. In short, decoding bridges the gap between binary language and meaningful hardware operations, making every CPU functions possible.
Thank you for watching our presentation on instruction decoder circuit design. We hope this helped you understand how opcodes are transformed into actions within a processor and how decoding forms the foundation of efficient CPU performance.